Hello, and welcome to Introduction to Large Language Models. In this video, you will learn to define large language models, describe LLM use cases, explain prompt tuning, and understand the difference between pre-training and fine-tuning a large language model. Large language models are a subset of deep learning. LLMs and generative AI intersect, and they are both part of deep learning. Another area of AI you may be hearing a lot about is generative AI. This is a type of artificial intelligence that can produce new content, including text, images, audio, and synthetic data. We'll explore more about generative AI in a different video. So, what are large language models? Large language models refer to large, general purpose language models that can be pre trained and then fine tuned for specific purposes. Now, what do pre trained and fine tuned mean? Imagine training a dog. Often, you train your dog basic commands such as sit, come, down, and stay. These commands are normally sufficient for everyday life and help your dog become a good canine citizen. However, if you need a special service dog, such as a police dog, a guide dog, or a hunting dog, you add some kind of special training. The similar idea applies to large language models. These models are trained for general purposes to solve common language problems such as text classification, question answering, document summarization, and text generation across industries. The model can then be tailored to solve specific problems in different fields such as retail, finance, and entertainment using a relatively small size of filled datasets. Let's further break down the concept into three major features of large language models. Large indicates two meanings. First is the enormous size of the training dataset, sometimes at the petabyte scale. Second, it refers to the parameter count. In ML, parameters are often called hyperparameters. Parameters are basically the memories and the knowledge that the machine learned from the model training. Parameters define the skill of a model in solving a problem such as predicting text. General purpose means that the model are sufficient to solve common problems. Two reasons led to this. First is the commonality of human language regardless of the specific tasks. And second is the resource restriction. Only certain organizations have the capability to train such large language models with huge data sets and a tremendous number of parameters. How about letting them create fundamental language models for others to use? This leads to the last point, pre-trained and then fine-tuned. Meaning to pre-train a large language model for a general purpose with a large data set and then fine-tune it for specific aims with a much smaller data set. The benefits of using large language models are straightforward. First, a single model can be used for different tasks. This is a dream come true. These language models that are trained with petabytes of data and billions of parameters are smart enough to solve different tasks, including language translation, sentence completion, text classification, question answering, and much more. Second, large language models require minimal field data when you tailor them to solve your specific problem. Large language models obtain decent performance even with little domain training data. In other words, they can be used for few shot or even zero shot scenarios. In machine learning, few shot refers to training a model with minimal data, and zero shot implies that a model can recognize things that have not explicitly been taught in the training before. Third, the performance of large language models is continuously growing when you add more data as well as parameters. Several large language models are available today, each with its own strengths and weaknesses. However, three of the most notable are LLaMA, PaLM, and GPT. Let's explore these models in more detail to understand how they differ. LLaMA, or Large Language Model Meta AI, is a powerful language model developed by Meta. With 70 billion parameters, LLaMA is designed to deliver high performance, Despite its relatively small size compared to some other large language models, it was trained on an impressive dataset containing 1.4 trillion tokens, which contributes to its robust language understanding and generation capabilities. Llama has several variants, including Llama 2, Llama 3, and specialized versions like Wizard LM, each building on the original model to offer enhancements and adaptations for different tasks and applications. PaLM, or Pathways Language Model, is a state of the art language model developed by Google. It boasts an enormous 540 billion parameters, making it one of the largest and most powerful language models to date. PaLM was trained on a vast dataset of 780 billion tokens, enabling it to achieve remarkable performance across a wide range of language tasks. Despite its large size, PaLM is designed to be highly efficient, leveraging Google's Pathways system to scale across multiple tasks and modalities. Several variants of PaLM have been developed, including PaLM 2, each iteration refining and enhancing the model's capabilities for specific applications. Finally, GPT, or Generative Pre-trained Transformer, is a groundbreaking language model developed by OpenAI. The GPT series has evolved significantly, with each version pushing the boundary of what language models can actually achieve. GPT-4, for instance, has 1.76 trillion parameters and was trained on a massive dataset containing hundreds or billions of paired tokens, enabling it to perform an impressive array of tasks, from text generation to translation and beyond. Despite its large size, GPT-4 is designed to be versatile, capable of handling various tasks with minimal fine-tuning. The GPT family includes earlier versions like GPT, GPT-2, as well as specialized models like Codex for coding, each building on the previous one to improve performance and expand functionality. All of these models are based upon a certain architecture called the transformer model. The transformer consists of two main components, the encoder and the decoder. The encoder takes in input data, processes it, and passes the encoded information to the decoder, which generates the desired output, like translating Spanish to English. But the transformer's capabilities go far beyond translation. It can generate images from text prompts, create videos, navigate within a game using only a prompt, generate music, or even produce an interactive game from an image. Essentially, it can take any input X and generate any output Y, whether it's audio, video, images, text, or code. We've come a long way from traditional programming to neural networks to generative models. In traditional programming, we used to have to hard code the rules for distinguishing a cat. In the wave of neural networks, we could give the network pictures of cats and dogs and ask, "Is this a cat?" And it would predict a cat. In the generative wave, we as users can generate our own content. Let's compare LLM development using pre-trained models with traditional ML development. First, with LLM development, you don't need to be an expert. You don't need training examples, and there is no need to train a model. All you need to do is think about prompt design, which is the process of creating a prompt that is clear, concise, and informative. It is an important part of natural language processing. In traditional machine learning, you need training examples to train a model. You also need compute time and hardware. Let's take a look at an example of a text generation use case. Question answering is a subfield of natural language processing that deals with the task of automatically answering questions posed in natural language. QS systems are typically trained on a large amount of text and code, and they are able to answer a wide range of questions, including factual, definitional, and opinion based questions. The key here is that you need domain knowledge to develop these question answering models. For example, domain knowledge is required to develop a question answering model for customer support, healthcare, or supply chain. Using generative QA, the model generates free text directly based on the context, and there is no need for domain knowledge. Let's look at three questions given to Gemini, which is a large language model chatbot developed by Google AI. The first question: this year's sales are $100,000. Expenses are $60,000. How much is the net profit? And Gemini first shares how the net profit is calculated and then performs the calculation. Then Gemini provides a definition of net profit. And then here's another question. Inventory on hand is 6,000 units. A new order requires 8,000 units. How many units do I need to fill to complete the order? And again, Gemini answers the question by performing the calculation. Now, last example, we have 1,000 sensors in 10 geographic regions. How many sensors do we need on average in each region? Gemini answers the question with an example of how to solve the problem and some additional context. In each of our questions, a desired response was obtained, and this is due to prompt design. Prompt design and prompt engineering are two very closely related concepts in natural language processing. Both involve the process of creating a prompt that is clear, concise, and informative. However, there are some key differences between the two. Prompt design is a process of creating a prompt that is tailored to the specific task that the system is being asked to perform. For example, if the system is being asked to translate a text from English to French, the prompt should be written in English and should specify that the translation should be in French. Prompt engineering is the process of creating a prompt that is designed to improve performance. This may involve using domain specific knowledge, providing examples of the desired output, or using keywords that are known to be effective for the specific system. Prompt design is a more general concept, while prompt engineering is a more specialized concept. Prompt design is essential, while prompt engineering is only necessary for systems that require a high degree of accuracy or performance. There are three kinds of large language models, namely generic language models, instruction tuned models, and dialogue tuned model. Each needs prompting in a different way. Generic language models predict the next word based on the language in the training data. This is an example of a generic language model. The next word is a token based on the language in the training data. In this example, the cat sat on. The next word should be the, and you can see that the is the most likely next word. Think of this type as an autocomplete in search. In instruction tuned models, the model is trained to predict a response to the instructions given in the input. For example, summarize a text of X. Generate a poem in the style of X. Give me a list of keywords based on semantic similarity for X. And in this example, classify the text into neutral, negative, or positive. In dialogue tuned models, the model is trained to have a dialogue by the next response. Dialogue tuned models are a special case of instruction tuned models where requests are typically framed as questions to a chatbot. Dialogue tuning is expected to be in the context of a longer, back and forth conversation and typically works better with natural questions like phrasings. Chain of thought reasoning is the observation that models are better at getting the right answer when they first output text that explains the reason for the answer. Let's look at the question. Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? This question is posed initially with no response. The model is less likely to get the correct answer directly. However, by the time the second question is asked, the output is more likely to end with the correct answer. A model that can do everything has practical limitations, and task specific tuning can make LLMs more reliable. You can also further tune the model by fine tuning, where you bring your own dataset and retrain the model by tuning every weight in the LLM. This requires a big training job and hosting your own fine tuned model. Here's an example of a medical foundation model trained on healthcare data. The tasks include question answering, image analysis, finding similar patients, and so forth. Fine tuning is expensive and not realistic in many cases. So, are there more efficient methods of tuning? And the answer is yes. Parameter efficient tuning methods, or PETMs, are methods for tuning a large language model on your own custom data without duplicating the model. The base model itself is not altered. Instead, a small number of add on layers are tuned, which can be swapped in and out at inference time. That's all for today. This video was largely inspired by Google Cloud Tech Introduction to Large Language Models video. I'll be releasing a more detailed video soon. Thank you so much for watching this video. If you found this video useful, then don't forget to like, subscribe, and hit the bell icon to stay updated. Have a good one.